about onboard mapping generation, which uses lightweight map priors to create a live HD map while the car is driving around. Onboard map generation is an AI model that is predicting roads, and if you train it with the right data and the right amount of data, it is able to generalize those regions it hasn't seen before on training.
ARM is the industry's highest performing and most power efficient compute platform with unmatched scale that touches 100% of the connected global population. Together with the world's largest computing ecosystem and 22 million software developers, ARM is building the future of AI. Hi, my name is Junko Yoshida. I'm the host of Junko's Talk to Us, and this is the AI from Toy to Tools video podcast series we have been doing. And today I'm with Ron Wilson, co-host of this series. Hi, Ron.
Hello.
Ron and I are really fortunate enough to interview Stefan Sellhusen. He is the director of engineering of automated driving at Bosch USA. Hi, Stefan.
Hi, Junko. Hi, Ron. It's a pleasure to be part of this podcast series.
This is actually a really great opportunity, having a tier one. And also, Bosch is also the developers of different sensing technologies. You have a system level knowledge, and yet you are here to talk about the use of AI in specific applications, in this case, mapping. I used to think mapping was already a solved problem, so I wasn't really paying attention to mapping. So let's start from where the mapping situation is in modern vehicles today. What kind of mapping are people using? What are the pros and cons? And where the industry wants to move?
Yeah, this is an excellent question. Maybe before we start, a quick introduction. So I'm located in Silicon Valley, leading the automated driving teams at Bosch. And we are here not just to pick up the latest technology trends, but actually to push the state of the art and in AI-based ADAS system. And this is one of the innovation you just mentioned that we will be talking about today, that we created together with our Bosch corporate research. And it's about onboard mapping generation, and which uses lightweight map priors to create a live HD map while the car is driving around. Before we come to that, maybe want to talk about the need. Why do we need maps in the vehicle? Right. So for a car to drive smoothly and safely, it can't just react to the traffic out there. It needs to anticipate. And the key part of this anticipation is the understanding of the road ahead beyond what the perception can see.
Right. What kind of maps regular cars are using? And there's a new generation of cars, such as maybe not that new anymore, but Blue Cruise and Super Cruise coming online. I think there's a changes in the type of mapping that the cars are using as the levels of the automation go up. So let's start with from the bottom and changes of the mapping systems.
That's an excellent question. So why do these self-driving systems need map first? So in order to drive smoothly and confident for the car, it can't just react, it needs to anticipate. And a key part of this anticipation is the understanding of the road ahead beyond what the perception system can see right now. And this is where maps come in. And traditional mapping approaches you just mentioned, they create a significant bottleneck because they are very expensive to create, and with that, not allowing these self-driving systems to scale effectively. And This is where we use this new innovation that is creating these HD map live in the vehicle while it's driving around. And with that, solving the challenge of having HD map in the car, but not at the crippling cost and maintenance that they bring.
Right. Okay. This is a good chance to talk about difference between SD map and HD map. What are the basic differences?
So you have the SD maps, which is basically what you use for your navigation app, for example. And that understands the road topology. It shows you how one road connects with another and allows you to reach your destination by just connecting the roads with each other. But what it doesn't show is how these lanes are connected individually.
Yeah, then, that I didn't know that. That I didn't. I thought that the maps are maps, but what you're saying is that the regular SD map does show the route, but it doesn't necessarily give you the level of details in terms of the lanes, how lanes are set up. Is that right? Is that
exactly? Okay. And then you have on the other side, you have the traditional HD maps. And those are created by these specialized survey vehicles. You might have seen some of these vehicles with a LiDAR on the rooftop driving around the city. And they are collecting these maps, and they are extremely precise in mapping those lanes. And they also create an understanding of the lane topology of your surroundings. And these are fantastic for automated driving. But they are expensive. They are time consuming to create. And they are outdated the moment a construction zone appears. Yeah. And this makes it difficult to scale these self-driving systems globally.
Right. So therefore, we are looking for the third way, which is something that's less expensive, but also more up-to-date, and something that your vehicle can handle without going all the way to the most expensive vehicle setup. Is that what you're saying?
Right. So we empower with this innovation the vehicle to create its own map layer in real time. And we do this by using standard camera images that are already on board for other ADAS functions. And they perceive the already lane boundaries and traffic signs and so on. And this means the car has always up-to-date map. And it's always fresh because it's generated right now.
Let me ask you this, that you said that these cars, regular cars, already have sensing system. I mean, they got cameras and stuff. Let's break down what are the technology building blocks to make this onboard mapping capability possible.
Absolutely. So creating a map just from the scratch, it's in many ways a more complex AI problem than the driving itself. Just look at the road geometry. It is illogical. It has been evolved over decades or centuries with constraints that are no longer visible anymore. Just an example, roads in Rome, in Italy, they are much harder to predict than in Phoenix, Arizona. So what we do—
That's a good one.
What we do is we just don't rely on the live perception. We use lightweight map priors. And you can think of it this way: a human driver with local knowledge is driving much more confident and smoothly than a tourist. And it's working because the human driver can anticipate tricky intersections or knows when a lane suddenly ends.
And in other words, like human drivers actually have the built-in lightweight prior in the brain because they've done it before, right?
Absolutely. They don't know the precise geometry of these mapping elements, but they know how the lanes connect. And this is exactly what we are talking about when I mean map priors. And we give the AI system this map prior knowledge, this local knowledge of the surroundings. And with that, giving the AI a powerful hint on how to connect maybe a lane from this side of the intersection with another lane on the other side of the intersection, and with that being able to navigate so complex urban scenarios.
Now, can you explain what kind of AI model can do that? I mean, did you build this AI model yourself?
So we use an existing transformer architecture that is using bird's eye view. And yeah, you can think of it in a way that there's a tiny drone hovering above your car, and it's capturing all the surroundings. And what actually happens is that the onboard cameras that the car has anyways for other ADAS functions, they're being fed into an image backbone of this architecture. And this image backbone extracts the visual features of it. And then these visual features are lifted up into the bird's eye view space. And this is not just rendering all the images and stitched together and a top-down, it's not just a top-down view, it's a spatially organized feature map. And in this bird's eye view, you can fuse these map priors into it. And that will help then in the second step when it's being decoded using the same transformer architecture to extract these map principles out of it. And like lane boundaries, lane dividers, pedestrian crossings, and creating out of that the map, the HD map with all the attributes that the self-driving system needs to work.
Interesting. So what you're saying is that there is a model called transformer, and the transformer allows you to stitch things together intelligently that what they see without having a drone hovering over your vehicle. AI actually does the job and putting all these things together as though it's not just the top-down view, as though actually it's seeing the whole thing from the drone's eyes. I mean, that's what transformer AI model does.
But with the difference that it's just not the image, the pure image that the cameras see. It sees with its own way. And this is what I meant in the beginning with extracting the visual features through this image backbone. And then you have this visual feature map spatially organized in the bird's eye view. And this this is optimized in a way that you have the utmost information that you would need to do the downstream task like a prediction or planning.
A lot of things it's doing then. I mean, it actually encompasses from leveraging the imaging information, extracting the information it needs to put them together, but also it actually spans to the actual driving instruction. Is that what you're saying?
Right. So what we are talking about in this architecture and what I just depicted, that is not showing the full details. For this, please have a look into the paper that was published last year. What we're talking about is how we generate these map features that are being used for downstream tasks like a prediction or planning further on. And these tasks, like planning, they provide the information to the actuators, like steering wheel and braking pedal, gas pedal, to how to control the vehicle longitudinal and lateral.
So this is something that previously cars were not able to do. I mean, cars are actually depending on the maps that it's given, but now you're saying car themselves can map the where it is driving.
Exactly. But with the catch that we use these lightweight map priors in order to help the car to map a more effective way and make it more accurate and reliable what the map that is being created actually brings.
So excuse me for my ignorance here, that where does that lightweight prior come from?
So that lightweight prior is that can be any type of like map. It could be a very easy road topology. And this is also what we have published last year. But you can also add more sophisticated attributes to it to give more powerful hints to the job to be done. And this would be then the lane topology. How are these lanes connected to each other? And that helps you to solve several problems. In in the world when it comes to navigating complex intersections, where you have to anticipate you need to take a certain left lane in order to do a left turn, which you don't see in the moment you have to take the left lane. And this is the local knowledge that we add to the system using these lightweight map priors. And as I said, it can be different level of quality information. And this is what it makes, depending on what OEMs would like to achieve with their functionality, can then be like used whatever it's they want to bring in, and with that deciding on having a more cost-sensitive system, which is just using SD maps, or if they are going more in the premium direction, having a high fidelity map information, feed it as a map prior.
Right. One of the things I'm thinking about is my own driving experience with SD maps. It seems like most of the time when it's going to tell me that I need to make a left turn, I hear about it either after I've already passed the end of the line of cars waiting to make the left turn, or at about the time there is a construction barrier in the left turn lane. So it sounds like you're saying that by fusing the camera data with the prior, you can deal with these problems uniformly.
Exactly. So this is what allows you to anticipate exactly these maneuvers you have to take before you come to these decisive actions that you need to take in the car.
So what happens then? I mean, assume that my car with this ability to generate the map real-time on board bumps into some kind of construction area, right? But the car understands, car sees the construction site and navigates safely through the area. That knowledge, will it be uploaded to the cloud somewhere to be shared with other vehicles? How does that work?
Yeah, that's an excellent question. We have maybe you've heard of the connected map services that we have at Bosch, which is actually using the cloud to collect map data from fleet and aggregating that data and then feeding it back into the vehicle to have a map based on crowdsourced. And we can use a similar mechanism to update the map priors using the same infrastructure, and by detecting differences of the map prior. And if the live system in the car doesn't, if it doesn't fit what the map prior is giving it, it is trained to, at the end, rely on the perception. So it's not like taking the map priors for given. But if there's a difference from what it got as a prior, it can detect the situation, and then it can also upload this data so that the map prior is correct for the next driver passing this.
It sounds like there's an important distinction there, that you're using the collected data to update the prior, not to retrain the transformer. So this isn't continuous learning in the traditional sense. This is updating the prior map.
This is actually we're doing both here. So on the one side, we're updating the map priors, but also with the collected data that we have from the crowdsourced mapping. So yes, we are using this as well for training data, and because this is a very valuable input for our training framework that is training this onboard mapping generation.
But I guess the difference, I think Ron asked you about whether you're just updating a prior knowledge or you're continuously learning. And that was his question. And your answer is that we're doing both. But my question is that the fundamental difference from the traditional connected vehicle service that you mentioned and this onboard mapping is that onboard mapping has the capability to generate map inside the car, while the traditional connected vehicle service is not doing that. Is that right?
Yeah, that's absolutely right. And this is what we've been also doing in the past. And there's both have their advantages in this. For example, the crowdsource mapping, you can get your data from the cloud. You don't need to have a powerful compute system in the vehicle to create it
Okay.
on board. So you can also use it for visualization here. On the other hand, even though it is already pretty fresh, the data that you get from these crowdsourced maps. So let's say within 24 hours, you can update your crowdsourced map based on what the fleet saw out there. You still have these 24 hours where the map is not up to date. And to also cover this is one of the benefits of using a HD map creation live in the vehicle.
Yeah.
Also, on top, you are able to also cover those regions where you don't have enough data to create a crowdsourced map. And the onboard map generation is an AI model that is predicting roads. And if you train it with the right data and the right amount of data, it is able to generalize those regions it hasn't seen before in training. And this is
coverage. That's so we talked about the coverage and expense and speed of the updates. I think these are all important elements. You know, let me ask you this. When I covered, you know, at Bosch, you call it the connected map services. That information, who has access to the data that was uploaded to the server somewhere? Is that Bosch's you know, only the vehicles that have a Bosch system can actually access to it? How does that work?
Mm-hmm. So for this, you need a huge fleet that is providing the data. And obviously, we at Bosch, we don't have, we are not an OEM. We don't have usually access to these end consumer vehicles that can upload the data. And what we do is we work together with other OEMs where we work in collaboration and get data to actually do this mapping in the cloud using the connected map services.
All right.
I guess that raises kind of an interesting question for me. If the system ends up in vehicles built by the OEMs that are going to be uploading data to a map database that you're maintaining in the cloud, how do you maintain security, since you aren't the ones who did the final design of the system that's doing the uploading?
Mm-hmm. Yeah, so this is done together with the OEMs in that case. So there's each company have their own security designs and also philosophy how to work with this data. This would take another podcast to talk about that details. And what I can say for sure that we at Bosch, we are taking safety and security of data very seriously.
You know, Ron always asks the security question, and most guests said, well, that will take another podcast, just you just said. And it's a difficult problem. I mean, it's the problem is there. We all know the problem is there. But again, that probably takes the whole different session. But you know, here's what I'd like to ask. I can't help but asking this question about the end-to-end AI versus modular AI. Part of the reason I ask is that I've heard people who are advocating end-to-end AI driving, such as Tesla's FSD. You know, if you look at some of what people are talking about in social media and stuff, they all say, oh, well, it's end-to-end. It's great because you don't need HD mapping. And I'm thinking, so really? They're not using HD mapping? And here you come. You say that you don't need HD mapping. Does that mean that your system is part of the end-to-end AI driving framework, or you're doing something different? Tell me.
Yeah. So maybe you need to clarify first. End-to-end AI driving, that can have different architectures.
Okay.
It can have modular architectures. It can also have monolithic architectures. Difference is monolithic architecture. Let's see it in a way that you take in the raw data from your perception, and the system learns how to control the vehicle actuators, steering, and acceleration. And that you can also see it as a black box. You don't know what the model inside, how it works, but it somehow is doing it. And you need a lot of training data to make every situation work. Then there's another approach. It's also called end-to-end AI, but a modular approach. And there you separate, you modularize your model in, for example, a perception part, a fusion part that is creating an environmental model of your surroundings, also using map. And this is where also the map is either feeded in or generated live. And then you have a prediction and a planning model that is taking this environmental information and creating behavior primitives, or actually the driving, the controls, the trajectory that is being used to control the actuators. And in this modular approach, you are able to look inside what each of these models are doing, and you can test each part of that model before you release it into the world on public roads. And that allows you to add additional validation layer in before you release your system into the market.
So in addition to validation, does that visibility in between modules also give you the opportunity to provide some feedback to the driver about what the system is thinking, if you will?
Oh, yeah, absolutely. So you can actually look into, you can visualize what the vehicle sees by using the outputs of the perception model, and you visualize that in your screen in the vehicle. And then you can not just provide an explanation of how the system works, you can also use these modular approaches to pre-train each of these models. You can tell the system how roads look like, how traffic signs look like, and with that giving it a prior knowledge to before you train the whole chain, what we then call end-to-end AI system that is trained end-to-end.
Yeah, interesting. That so the terminology you use is there are two systems over the overarching end-to-end concept. One is a monolithic, another one is modular, correct? And so when we talk about the onboard mapping generation that your system allows, that's part of the modular approach, correct?
That's correct. That's correct. And I see where you're going, is that the monolithic approach, it doesn't need HD maps, and that's correct. So, but on the other side, you need much more data to make the system figure out, just based on sensor data and what it is supposed to do in the car, what is a traffic light. And there could be some tricky situations, like it starts decelerating. So imagine we're approaching a traffic light that is red, and there are vehicles standing in front of it, or there's a leading vehicle in front of us that is decelerating. So the model can mistakenly learn from the car in front of us that it has to decelerate because the car in front of us is stopping, because the car in front of us knows there's a red light, it has to stop at the stoplight. But if there's no car in front of us, and the system only relied on learning from a car in front of it, it is passing the red light because it didn't know better. So you need to have enough data, training data, to make sure the system knows all these different combinations of situations worldwide. And this makes it difficult to foresee all the different corner cases that are out there to ensure that the system is working.
Speaking of which, I don't mean to put Tesla on the spot, but this has just happened to the story I recently wrote. So I'm going to bring that as an example that Tesla started the robotaxi operation in Austin, Texas. And there was an incident, I think there are a couple of them actually. There was an incident that Tesla robotaxi did not recognize two left turning lanes that going this way. And Tesla also wanted to go turn left, but obviously it missed those clearly marked two turning lanes. Part of the problem is that I think this is actually often done in Austin, that there's not a huge concrete barrier, not the tall one, but the small one is actually between the lane that goes straight and two lanes going to the left. So obviously this robotaxi missed the turning lanes, but it still wanted to go to the left. So go to the next intersection and force itself, even though it's illegal to turn left, turns left. Luckily, nothing happened, but actually the car kind of stops in the middle of the intersection in T-bone zone. But nothing bad happened. Okay. So the problem is that since we talked about prior knowledge, and if I were a driver living in Austin, I do know this. This is like I've seen this kind of setup. How is so having no HD map, no prior knowledge? I mean, is that one of the problems you guys can solve? I mean, tell me a little bit about your thoughts on how it doesn't matter which car it is. How would you solve that kind of problem?
Mm-hmm. Yeah, that's actually a very fitting example to what we just spoke about, how OMG or onboard map generation with map priors can help you to overcome these tricky intersections and to navigate through them. And obviously there are different philosophies out there how to build architecture and what to use in order to drive through or to build your system. And there are philosophies out there that say, well, we really don't want to use any map priors because this makes my system depending on maps. And you could also do it with just your live perception, because there are also tourists able to drive safely in these scenarios. So you need to, if you don't use any prior map knowledge or local knowledge, you need to train your driver that it can get this information in some other way. And what we propose with using these lightweight map priors is to take this prior knowledge into account to then being able to cross the intersection more confident, and of course taking the right turns when we are supposed to.
Something I've been curious about, I guess when I hear the word transformer model, I start thinking enormous. What size system in terms of processing power and memory requirements are we talking about here? Is this going to require a rack of servers in the trunk, or are we talking about a single SoC on a board? Or
yeah, so that's a good question. So yeah, obviously you can't put a server in the trunk for an end consumer car, and these architectures, they need to be transferable onto an embedded target, whatever the OEM is choosing. And it's amazing how much computing power latest SoCs already have, and they are capable to host a powerful transformer architecture with a bird's eye view on it. And that is what I also see where the industry is converging to, using these transformer architectures and putting them onto different kinds of SoCs. Of course, there are different SoCs, one more expensive, have more computing powers as the others. You have to adapt your architecture according to what the SoC is providing you in terms of computing power, and maybe also specialized instruction sets that allows you to optimize your function specifically. And this is also a topic that you can spend another podcast on, going into the details.
Could you give me some idea of what the range is? If a modest SoC is the bottom end of the range, what's the top end that you're actually seeing in development among the OEMs?
So we see a very wide variety of SoCs being used by different types of OEMs. Especially in China, we see that there are very expensive SoCs being used with a lot of computation power. Whereas outside of China, I would say, we see more modest SoC with computation power of maybe 20 to 100 tops. And the challenge is to bring these architectures also into the less computation powerful SoCs.
No, that's fascinating. So this is I want to close the session talking about, I think you already touched upon, is the scalability. If I'm OEM, I'm worried about scalability. I like your system. I'm not sure I can use the same system to my 3 different models. How do you help me?
So just when we keep to the mapping problem, we already scale by not relying on HD maps, which are expensive to create, which might be outdated. So we already have a big win with the onboard map generation. And then scaling it to different OEMs, different regions, this is a huge problem to solve for us as being a tier 1 who has to provide solutions for all the customers out there. But the cool thing is we are in the middle of all these different requirements and different product ideas that the OEMs have. And we can leverage the data that we get from all these projects to build a system that is able to scale multi-SoC, multi-region, multi-trim levels, what we call internally, for different levels of feature set. And this is actually what puts us in a good position to support OEMs to bring a solution that is not just scaling, but is also competitive, because we don't do it once for one scenario. We reuse the assets that we have from different projects, and with that being able to provide a competitive ADAS solution.
Right. Yeah, that's the heart of the tier 1's job. So how many, you don't have to name names, but how many vehicle vendors, OEMs, are already using your onboard mapping system today?
So this is a innovation that recently came out. We're working on with different OEMs to make that reality. And the system, as I described it, is going to be out soon.
Out soon. 2026?
I can't talk about that.
All right. Yeah, I was getting ahead of myself. Well, I can't wait to see that happen. So probably you will show this off at coming various auto shows, correct?
Maybe, yeah.
I love talking to engineers, like engineers don't make things up, Thank you. But thank you for your honesty. I appreciate it. And I hope we can get back. I hope we have a chance to see each other, and the sort of further discussion. We can have further discussions. Thanks for your time, Stefan.
Well, thanks for having me. It was a great experience.
Yeah, thanks. ARM is the industry's highest performing and most power efficient compute platform with unmatched scale that touches
100% of the connected global population. Together with the world's largest computing ecosystem and 22 million software developers, ARM is building the future of AI.